So hello everyone, welcome to this Men&Mice webinar. My name is Peter Petersson and with me today is Carsten Strodman. Carsten, can you present yourself?
Yes, hello. I'm Carsten. I'm working at the Men&Mice professional team, and I appear occasionally on these webinars to tell about exciting stuff around DNS.
And talking about exciting stuff, Carsten, I think we have quite exciting DNS stuff here today, how to send DNS over anything. I'm curious to learn more about this mystical subject. But before we start, please note all attendees that you're on mute, but I encourage you to submit your questions at any time through the GoToMeeting control panel, and we will address these questions toward the end of the webinar. We are also recording this session, so if you drop off for any reason during the webinar, you can still come back and find the webinar at our website and the slides within a few days. So without further delay, Carsten, the audience is yours.
Thank you, Peter. Hello, everybody. Welcome for our today's webinar on how to send DNS over anything encrypted. So what does it mean? I will mainly talking about the work of the DNS-Privacy group inside the IETF, because there a number of people have created new protocols or protocol suggestions, which are currently internet drafts, about how to encrypt DNS. And the reason here, which I dive in later, is about privacy. That is, make it harder for anyone not permitted to see the data to snoop on the data. We will talk about various things, and it seems to be that development of the DNS protocol in the IETF takes a waveform. Sometimes it's very quiet, some years are very quiet and nothing much happens in the DNS working groups at the IETF, and other years, like this year, a lot of stuff happens and a lot of new protocol and RFCs coming out of the working groups. And I want to give you an overview on what's already available, what's on the horizon, and what we can expect in the future, and maybe what we will see in production in 2 or 3 years from now. So this is the protocols I will talk about, and let's just roll in. One more note here. There's even so much work going on, DNS over something encrypted, in the IETF, that some member of the IETF working group suggested to create a new working group with the title DNS over New Transport Protocol, with a nice acronym of DON'T. And there's a message here. So first about DNS privacy. The IETF started the DNS privacy working group just after the Snowden revelations. Actually, it wasn't really triggered by the Snowden revelations, because there was already plans to do DNS privacy work inside the IETF, but the information that Snowden revealed just speeded up the whole process. And there is an RFC that explains the DNS privacy considerations, RFC 7626, which is all about what privacy implications today's DNS has and where the problems are. What shows inside the IETF, and especially I found that during the latest IETF meeting in Prague, which was in July this summer, is that creating protocols that are stealthy, that are resilient against snooping and surveillance, sometimes painfully collides with clean protocol designs, because sometimes in order to be sneaky and stealthy, you have to hide stuff. And if you hide something, maybe hide something inside another protocol, that's not clean, that's not clean protocol design. And people in the IETF have sometimes a hard time learning this and creating these new protocols. So the first protocol we will look into is DNS-over-TLS. TLS, that is transport layer security, which is the same security technology that we all know and love from the web. So if you go to a website and your URL starts with HTTPS, S stands for security here, that means you're using transport layer security, which is the new name for something that Netscape invented back in the 1990s with the name SSL, Secure Socket Layer. Now it's TLS, but it's technically the same stuff, just a little bit modernized. This proposal, or this RC, it's already standardized, explains how to send DNS-Wireformat, that is the same data that we have today over UDP and over UDP and TCP, just over TCP and TLS, and the specification reserves port 853 TCP for that purpose. DNS-over-TLS both gets us encryption and authentication. So the DNS data is being encrypted, so nobody can really read what's being sent here. And also the two endpoints are authenticated so that the client knows that it talks to the right DNS resolver. Okay, at this point of time, I should point out that all the work the DNS privacy working group currently does is to secure the transport from a client to a DNS resolver, not between a DNS resolver and an authoritative server, because the traffic being sent between a client and a resolver is more privacy sensitive than the other data. If the way between client and resolver is being secured, then the working group will recharter, and so we'll probably tackle the transport between a resolver and an authoritative server. So the performance of DNS over TLS can be quite good. So tests, especially with the new TLS 1.3, which is being also deployed right now, shows that it can be as good as the old DNS over UDP. So how can that be? Because there must be overhead, because it's not UDP anymore, it's TCP, and then we have all these crypto stuff in there and encryption and so. It can be as fast because TLS 1.3 implements pipelining, which means that queries and answers can be sent out of order. There's nothing that is called ahead of line blocking. So a DNS client can just send DNS queries in any order as fast as it can through the same pipes, through the same open TLS channel, and then the resolver can just send answers whenever the answer is available. There's no need to first send a query and then send the answer and then wait for the second query until the first query is answered, but the client can just do that out of order, and the server can also answer out of order. That makes it quite fast. Then it implements TCP fast open, which means that the two communication endpoints can already send data in the three-way handshake. So with TCP, we have the three-way handshake, which is a SYN, SYNACK, and ACK. So the client first asks the server, can I talk to you? And then the server responds back, sure, I'm ready. Will you talk to me? And then the client says, yes, here I come. And this three-way handshake originally with TCP is without data. So it's just three packets flowing back and forth to make the session. And then the data is being sent. Now, opening a TCP session, then sending data, and then closing down the session with another three packets going back and forth, that would be wasteful for DNS. So TCP fast open allows already to send the DNS query, for example, over the three-way handshake. And then we have zero RTT resume, which means that usually a client will keep the TCP and TLS connection open to its resolvers, because a client only has a handful of resolvers configured. Under Unix, we have usually the limitation of 3 resolvers. Under Windows, we have a little bit more, but anyway, it's not more than 10 in most cases. So it's not much resources being used at the client side, so the client can just keep the sessions open. However, a server might get in resource problems when it has a lot of, like, multiple thousand of clients keeping TCP connections open. So the server might just close the connection in order to free up some resources to handle other clients. In that case, the client can just resume a previously existing session by using the same crypto parameters as before, and that is 0 RTT resume, meaning that there is no extra setup cost for reopening the channel. However, current implementations, that is implementations that we can install and deploy today, are not that optimized and not using TLS 1.3. And we will see some numbers, performance numbers of DNS over TLS at the end of this webinar. So which implementations do we have today? There is Unbound on the client side. So Unbound can be used as a local forwarding resolver that you can install on your laptop or desktop or Windows machine, and that will take locally on the loopback interface all the DNS queries and wrap that into TCP and TLS and forward that to a real DNS resolver, which then works like normal. And then there's Stubby, which is part of the Get DNS API. And Stubby is a special stub resolver, and it is the replacement of the old stub resolver we know from Unix and Windows machines. Stubby is so interesting that we will probably make a webinar all on its own what Stubby can do, because it not only implements DNS over TLS, but also a lot of more modern DNS stuff that is currently unavailable for client machines and client operating systems. And Stubby is about to change that. And then we have DNS FWD, which is the DNS forwarder, which is an experimental piece of code that already implements pipelining and other performance improvements on the client side. And on the server side, there's Unbound as a remote resolver. There's the NOT resolver that can be used, and we can use any DNS server with the help of S-Tunnel. So S-Tunnel is a tool that is available on Unix and I think also on Windows, which can be used to turn any application that talks over TCP into an application that talks over TLS. So if you have a bind name server or a Microsoft DNS server and you want to make that server available over TLS, you can just install S-Tunnel on the same machine, configure S-Tunnel to accept connections on port 853 and forward all the unencrypted data locally to port 53 TCP. And that works just fine. And the good folks at IEC, they have an tutorial on how to do that with bind on their knowledge base. So what are the current developments in that space? DNS over TLS is an RFC already. So that work in the IETF has been done. However, there are some roadblocks with TLS 1.3. So DNS over TLS works fine with TLS 1.2 and 1.1, but 1.3 is currently stalled because there are some misbehaving middle boxes. Especially one name is often being called its Blue Code. Blue Code is a company that sells deep packet inspection devices which try to break encryption and look into the data. And in these boxes, if they see TLS 1.3, maybe because they cannot open, because it's too good encrypted, they just block the data and drop it on the floor, which means that even good use of these devices result in no connectivity. And the IETF and vendors are currently working to solve this problem. Also controversial in the IETF, but very useful, is you can multiplex HTTPS and DNS on port 443. So even though the IETF has reserved port 853 for DNS over TLS, nothing is stopping an operator to configure a DNS server to work on port 443. Why should the operator do that? Now, because in firewalls, port 443, which is used for HTTPS, is almost open universally. It's available in internet cafes and hotels and so on. While port 853, because it's so new, it might be blocked in the firewall. So in order to circumvent that firewall blocking, DNS traffic can be sent over the HTTPS port. Now, next is the problem if you already have a web server running and you only have one machine. What do? Now, there is a tool called HDDMux, which is a multiplexing software that detects on the first bytes of the first handshake package whether the data will be HTTPS or will be DNS-over-TLS, and then diverts the data either to a web server or to a DNS server. And so you can serve a website on port 443, and you can have your DNS servers running on the same port. Isn't that cool? This was one of the discussions in the IETF that was painful, because a lot of people thought that is not clean protocol design, which is true, but sometimes you need to go out of the box in order to create security. So next topic is DNS-over-DTLS. The D stands for datagram TLS, and datagram is the little brother of the bigger TLS, which is basically the same encryption protocol that we know as TLS, but over UDP. So this is DNS-Wireformat-over-TLS over UDP, using the same port 853 UDP, and also provides encryption and authentication. So why do we need that if we have the other? Not really sure, because DNS-over-DTLS has some issues. Both protocols have been developed simultaneously at the IETF, and they have almost been simultaneously being published as an RFC. But the problem with DNS-over-DTLS is that an adversary can block DNS queries. So the bad guy operating the firewall or doing privacy snooping can just block the UDP queries, and the client will never know. If you block TCP, then the handshake fails and the client knows. But with UDP, it's just a package being sent, and if that is being dropped in the firewall, the client needs to resend and resend and resend, and that takes time. Also, with DTLS, there are resource exhaustion attacks possible with DTLS because of the UDP nature. It's possible to just spoof the sender address. The same problem we have in DNS with the reflection attacks. So that's problematic, and there are some solutions here, but because most of the time the solution is, if it doesn't work over UDP, then we have to switch to TCP. And because of that, the operators say, hey, if we need to implement DNS over TCP over TLS, then why also implement DNS over DTLS? Let's go with DNS over TLS in the first place. And that's the reason why, at least I don't know any implementations that are available for DNS over DTLS. Next, we have DNS over HTTPS. Now, the difference here is, while the previous two formats were sending the DNS wire format, the same data that is being sent over UDP today, this protocol uses the HTTP format. So on the wire, it looks really like a web browser requesting data and a web server sending data, instead of a DNS client talking to a DNS server. This is not an RFC. It's currently an internet draft. It means it is something that is being worked on in the IETF. It might become an RFC, or it might just die if there's not enough interest in bringing this forward. So currently on this one, there is quite a lot of interest to bring this forward. So I foresee that this will become an RFC at one point of time in the future. Now, this protocol draft specifies port 443, the normal HTTP port for sending, and the DNS communication is being done with a well-known URL. So it's HTTPS:// and then the server's name /.wellknown/DNS query. And then you send the DNS queries there as base 64 URL encoded DNS data, with the content header application DNS-UDP wire format. And that also allows for encryption and authentication, but this is now the same encryption and authentication that we know between a web browser and a web server. There's nothing special here. The same code can be used, the same libraries can be used that are already being used in web browsers and web servers, which is nice because these libraries are already well known, well audited, and available. Also good with this is that it works over port 443, so it also works in heavily firewalled networks. And this is very easy to implement for web developers, because with JavaScript or any of the other active components within a web browser, you can talk HTTP over port 443. There's nothing special here. So if a web application wants to do a DNS query, which is quite hard today, not so much for address queries, like you can query for IPv4 and IPv6 addresses from a web application, but for example, asking for, let's say, SRV records or TXT records, that's quite difficult without extra components and extra help and extra middleware. That is now quite easy to do with DNS over HTTPS. There is additional work going on in the IETF, because sending the data over transport is one, but the other question is how to encode the DNS traffic. And there is one draft that talks about representing the DNS messages as JSON, which is currently being worked on. And there's an older one, DNS messages as XML, which is currently expired. It seems to be that nowadays XML is a little bit out of favor and JSON is the new kid on the block to be used. Google already implemented a very similar service. It's not identical to what's being described in the internet draft, but it's very, very similar. So on the server side, the Google public DNS, they have the ability to query or use the public Google DNS server over HTTP, and the documentation for that is on this link here, the Google DNS server side. And there are two client-side implementations. There's Dingo, which is a DNS client written in Go that resolves DNS names via the Google DNS over HTTP servers. And there is Core DNS, which is one part of cloud and container-based DNS solutions being used in cloud deployments. And that is also using the Google DNS over HTTP implementation. So next we look at DNS-Wireformat-over-HTTPS. And that is very similar to what we have seen before with the DNS over HTTPS. The difference here is that the data is not being encoded in JSON or XML or as a normal HTTP request, but instead the data is directly sent with HTTP 1.1 or HTTP 2 over port 80 or port 443. So while the other protocol standards and specifications that I'm presenting here always encrypt, this is the only one where encryption is optional. So it can be sent over port 80, which is unencrypted, or port 443, which is HTTPS, which is encrypted. It works with a different URL, which is HTTPS server name .wellknown -DNS/wireformat. And the content header is also application DNS-Wireformat. And it may provide encryption and authentication, but it's not mandatory. So what's happening here is that the DNS-Wireformat is wrapped in an HTTP header and then transmitted over. And that actually works because HTTP is a very forgiving protocol or very open protocol, so that you don't even need to speak real HTTP on the port to get along with sending the data over port 80 or port 443. And now we come to DNS-over-QUIC, where QUIC is a new transport protocol developed originally at Google and it's being now standardized inside the IETF. And what's nice about QUIC is that QUIC feels like TCP, but a modern TCP. So it has all the session and the congestion control that we know from TCP, but it's based on UDP. So it has the agility of UDP while having the good parts from TCP, even modernized. So there's quite a fuss over QUIC in the IETF at the moment, and a lot of people love it because it seems to be the best of both worlds, UDP and TCP together, and we have QUIC. And now, of course, we need DNS over QUIC connections, which is the draft here, which is currently a personal draft by Christian Huitema, but will probably progress to be a working group adopted draft in the future. So QUIC is, as I told you, a modern TCP replacement from Google, now standardized in the IETF. It is usually implemented in applications, not in the operating system kernel. So we have it in browsers. We have it in then a DNS server or in a DNS tab resolver like Stubby. Currently, it's implemented in the Google Chrome browser and descendants from that. So Opera, Vivaldi, and Safari, I'm not sure, maybe others. It already includes TLS 1.3, and it also has the 0 round-trip time session resume. Performance in early tests showed that DNS over QUIC is in par, so it's equal with DNS over UDP. And if you are interested in reading more about QUIC, here's a link to the QUIC document at the IETF working group. This is a chart I've taken from Christian Huitema's presentation at the IETF in Prague, and it compares the classic UDP TCP DNS with TLS, DTLS, and QUIC. And as you see, QUIC is the best of all because it has no red marks here and all green checks. So it has very fast connection setup time, 0 round-trip time, except for the very first connection. It has no head of queue blocking. It is efficient in retransmissions, which is not the case with the UDP protocols. It allows for long and big answers, important for DNSSEC. It has the 3-way handshake, and it offers encryption and authentication. So it's too good to be true. We don't know, but it's exciting. And then we have DNS over-opportunistic IPSEC. And that means that we send DNS over UDP and TCP just as normal, but UDP and TCP are then protected by IPSEC. So instead of sending over a clear IP protocol, we're using IPSEC, which is on a different layer. That provides encryption, but only limited authentication if we use opportunistic IPSEC. Unauthenticated opportunistic IPSEC is already implemented in LibreSwan, which is the IPSEC implementation done by Red Hat. So if you have a Red Hat Linux operating system, you can already use that from LibreSwan. And there is a module, an IPSEC module from Unbound that supports the LibreSwan implementation. So what's going on here is that if Unbound is being used as a DNS client forwarder, and it needs to talk to some remote DNS resolver, then it first looks up the IPSEC resource record in DNS, which can be used to deliver the crypto configuration for an IPSEC tunnel. And if there is an IPSEC DNS information, then it will use that setup data that is being returned to create an IPSEC tunnel to that resolver, keeps the tunnel open, and send then all DNS traffic encrypted. And Unbound can be configured to not send any data if the setup of the IPSEC tunnel fails. IPSEC in the past had problems with heavy firewalling because the setup, especially using the IKE daemon, which is the Internet Key Exchange, that worked over UDP, over dedicated ports, and these dedicated ports are often blocked in firewalls. So opportunistic IPSEC wasn't really working because there was too heavy blocking with firewalls. Now, with RFC 8229, we have TCP encapsulation of IKE and IPSEC packets, which allows now IPSEC to completely work over TCP and also work on over any port TCP. That means that we now can send IPSEC over port TCP 443, which is the HTTPS port, which is often non-blocked, not blocked in firewalls. And that can even be multiplexed with HTTPS. So we can still use web browsing over port 443, run a website there, and have an IPSEC endpoint on the same. So we see that port 443 HTTPS is the universal new protocol everyone uses. So all the stuff now we've talked, or I've talked about, is the work inside the IETF. And now we have some more protocols that are developed outside the IETF but tackle the same problems. And the first is DNS over DNSCrypt. DNSCrypt is a privacy solution originally developed by the people from OpenDNS, which is now part of Cisco. It provides encryption and authentication. The protocol itself is open source. The client is open source, but it's somewhat under-documented. So there's not much documentation how the protocol really works, and other than the source code. So if you really want to know if it is secure, you have to understand and read the C source code to maybe implement that yourself or have trust in the solution. The client operates as a DNS proxy, meaning that you install the DNSCrypt client as a proxy on your machine. You configure your resolve.conf or TCP/IP configuration in Windows to send all the DNS queries over UDP to a loopback address. On that loopback address, the DNSCrypt proxy will take the data, encrypt everything, and send that over to a DNSCrypt resolver. Some, but not all, DNSCrypt resolvers available in the internet support DNSSEC. So if you need DNSSEC, and I would highly recommend that, you have to pick those resolvers that support it. Then we have DNS over Tor, Tor being the onion router. And that is a privacy and anonymity software that is being used for like browsing the web in anonymous fashion. It works by creating a circuit of multiple so-called relay hosts, and your client will talk to a Tor machine that is somewhere in the internet that's called the entry node. That machine will encapsulate, or your client will encapsulate the data and encrypt the data. The entry node and the relay node will forward the traffic to what's called an exit node, and then the exit node will send the data out to the real internet, unencrypted. And on the way back, it goes the same way through 3 relay nodes, entry nodes back to your client. And by sending it through this Tor circuit, it's impossible for the entry node to know where the query destined, also where it's going to, and the exit node doesn't know who originally has sent this query. So the exit node sees the query, sees what's being requested, but doesn't know who has sent this. So it provides anonymity. The downside of Tor, and especially DNS over Tor, is that it only supports IPv4A records and IPv6 quad A records, but nothing else. So no TXT, MX records, SOA records whatsoever, including no DNSSEC records. So you cannot do DNSSEC if you use Tor and send your DNS traffic also over Tor, which is problematic because we know that Tor exit nodes are operated by government agencies, and also Tor exit nodes can be operated by criminal entities. So they might spoof the DNS traffic, and if they do, and you don't use DNSSEC, you never know. So you're getting wrong DNS data, and you have no chance to see that. Also, a recent study has found that over 30% of the Tor exit nodes use Google Public DNS for their DNS resolution, which means that Google sees more than 30% of all the Tor DNS traffic. which might bring Google in a perfect position to de-anonymize and the traffic, and maybe do some traffic analysis and snooping on that. Not so good for privacy. If we encrypt DNS traffic in any of the protocols that I've shown before, there's always the problem that DNS data has a very distinct fingerprint. It is small queries going out and a little bit larger, but still small answers coming back. So just by looking on the query responses of these small data chunks, a surveillance operation might detect from the package size that this is DNS traffic that's going on through. They cannot see what's in the queries, but they see it's DNS. In order to make traffic analysis a little bit harder on this, the IETF is currently working on padding schemes for DNS to make this traffic analysis more difficult. Padding basically means to put extra random stuff in DNS queries and DNS answers that don't belong there, that have no other meaning than make the package a little bit bigger and maybe make the packages look like more web traffic. And there's already in RC the eDNS0 padding option, which allows us to stuff extra data, nonsense data, random data in an eDNS0 option. And the IETF is now working for padding policies, which are basically some baseline padding ideas that operators can implement in their software. So now the big question is, what about the performance? Now, what happens if we encrypt DNS traffic and send it over TCP instead of using UDP unencrypted? Isn't that painfully slow compared to the DNS that we have today? I was curious and I set up a test lab, and I used the Alexa top 1000 domains and tested them against all these different setups. And here's the results. In this test, what I've done is in the beginning of the test, I've cleared all the caches. And then I send with the script 1000 queries for an A record, for an IPv4 A record, towards all the domain names listed in the Alexa top 1000 list. And I timed how long it takes to resolve all the 1000 domains. Because all the domains are different, there is no caching happening here at all. And because of that, we have all the stuff that works through Unbound is not as fast as it could be. So the first line is the Google public DNS over UDP, non-encrypted, no privacy, but we have DNSSEC somewhat there. And Google DNS from my test lab could resolve all the 1000 domains in 64 seconds. DNS-over-TLS came already in as second. So that was with the DNS forwarder and S-tunnel towards a public DNS-over-TLS resolver in the Netherlands, operated by Surfnet. Thanks the good guys from Surfnet for making that possible. And that was in 67 seconds. That has all the privacy. Unfortunately, if you just have DNS FWD with S-tunnel, you don't have any DNSSEC validation locally. Then we have local Unbound without DNSSEC and with DNSSEC, DNS over DNSCrypt, using one DNS server from Iceland. That was just randomly chosen, but it chose one from Iceland. It could have chosen one from Australia or Peru. That has privacy and DNSSEC, so that is the first solution that really is good from the privacy point of view. But 243 seconds compared to 64 seconds, it's not good. And we see all the other DNS over TLS is even worse, because the implementations are currently not optimized. So it's not using TLS 1.3. It hasn't the ahead of line blocking and zero round trip time resume and such. But this test was rather artificial. Nobody resolves 1000 unique domains in a short amount of time. So I did a more realistic test. So I collected 1,000 DNS queries from an office network. So I used TCP dump. I collected just the DNS queries going on in a normal office network here. And then I replayed that queries to the different protocol and setups. And here, because it is just the DNS traffic being captured from the network, we have caching in effect. And this shows that now, because we have caching and we have caching locally, DNS-over-TLS with unbound forwarding to DNS-FWD and using S-tunnel is the fastest solution because 1,000 queries just take 10 seconds to resolve, and we have all the privacy and we have DNSSEC. Second, just a second slower is a local unbound with DNSSEC or without DNSSEC. There was no difference if you have caching enabled. Then there is 2 times DNS-over-TLS, one time without unbound, the other time unbound just with S-tunnel, and then comes Google DNS in with the old UDP. And this is because there's no caching going on if you use Google DNS without a local caching resolver. If you point your etcresolve.conf directly to 8.8.8.8. So from performance, that's not the best solution you can do. And the other DNS-over-TLS was the unbound built-in TLS. DNS-over-DNSCrypt and DNS-over-Tor are much slower than the others. So we see that DNS-over-TLS in a realistic office network solution can work. And that is where we want to have the privacy. Where I wouldn't recommend DNS-over-TLS at the moment is, for example, in a DNS resolver for a mail server. There's probably not so much privacy gained there because that's all queries about some spam blacklisting or whitelisting. But in an office network or in a private home network, you want to have the privacy and you want to have your DNS traffic encrypted. So here's the link list about the DNS privacy project, about the various RFC, the HDDMUX source code from Daniel Kahn-Gilmore, DNSCrypt, where you can find the DNSCrypt proxy source code, the DNSCrypt resolver if you want to run your own resolver. There's even GUI DNSCrypt for Windows and for Mac, and you can do more with DNSCrypt. For example, you can do spam blacklisting or a malicious website blacklisting as well with DNSCrypt, which is a positive side effect. And about the Tor project and the study about that 30% of all Tor exit nodes use Google DNS, and the DNS-FWD, the DNS-over-TLS forwarder source code. You find it there on GitHub. So this is the end of the meat section. Now comes a little bit what is next at Men&Mice. So we have one open DNS training, which can be done or will be done in Zurich next week. We have also the advanced class there, and we have a DNSSEC and DNS or DNSSEC in Dane and DNS class in Linux Hotel in December. And we are currently working on getting the Men&Mice DNS trainings online, and look out for some announcement in the future there. Probably in the time frame November, December, we will make that more public, where you can have our DNS trainings online and in any pace you want. So I'm done. Do you have questions?
So Carsten, I see no questions yet, so we can give the attendees maybe 1 or 2 minutes to think about it. But these sounds like exciting protocols you're presenting there from the creative people, you know, in these IETF meetings. But if you take a second look at this, how would you place your bet? Which one of these do you think make it through as industry standards?
My gut feeling is that we will see DNS over QUIC because it's Google. Because Google has the power to just push it out to the market, to implement it in the Chrome browser. And if it is in the Chrome browser, it has such a market power that others will be forced to follow through. So we will probably see Mozilla with Firefox and others to also implement that. But that is maybe good for Google, but maybe not so good for privacy, because then the traffic is encrypted, which is good, but all the traffic is being sent to Google, which is maybe not the best solution for privacy. We will probably see some DNS over TLS deployments. And I'm currently trying to make the operators of DNS resolvers, especially the people who operate access networks, like the cable companies and the old incumbent telecoms in Europe, on others ISPs, make them aware of this. Because if they don't act now, if they don't implement DNS over TLS on their resolvers, offer this solution, they will be cut out of the game. Because if DNS over TLS is not implemented on their resolvers, we will just see Google implementing that on the appliance side. And then all the DNS traffic bypasses their resolvers and go directly to Google or other DNS resolvers in the internet, which is not perfect in case of traffic engineering and performance latency and such. You want your DNS resolvers close to your machines. And if you are in a home network and if you work within a trusted operator, you want your DNS queries being resolved in that network. Or even better, you implement your own resolver by installing Unbound there. But most people don't. So for the most of the internet population, it would be good if the operators of DNS resolvers will notice and will implement DNS over TLS. But I fear they won't, not enough. So we will see DNS over QUIC being the major protocol being implemented, and DNS over HTTP. That will be done for the web applications, because we have so many web applications nowadays, and they can run in the cloud. It's just convenient for the developers, and the developers will jump on this and will do it.
Very good. I see no other questions yet from the audience, but it was a really impressive presentation, and the performance analysis quite interesting as well. So, Carsten, if there are no further questions from the audience, I would just like to thank you for your presentation today, and thank everyone attending as well, and remind you that we will put the recording on our website. So if you want to take a closer look at the slides or anything else, or just take a look at anything else you find on our website, our nice IP address management solution, or any other stuff we have there, or the trainings, DNS trainings we have as well. So you're always welcome there. But until next time, thank you very much.
Thank you. Bye for now.